So let's now look at how inverse trigonometric functions and trigonometric functions work whenever we compose them. So if we take our composition of functions that we know about from a previous unit, where we take f of g of x or g of f of x, well, what would it look like if we took sine of arc cosine of some input, or some combination of those? So as we look at our composition of functions, it will be important to remember the range restrictions of the inverse trigonometric functions. So remember that arc sine outputs values between negative pi over 2 and pi over 2 inclusive. Arc cosine outputs values between 0 and pi inclusive. And arc tangent outputs values between negative pi over 2 and pi over 2. And then to help us out, I like to look at a diagram such as this that I introduced in the previous video. The key thing to remember is that the input of an inverse trigonometric function is a ratio. And as we output an inverse trigonometric function, it will have a restriction on what type of angle it can be. So let's take a look at our first example, cosine of arc cosine of 1/2. Let's begin by doing this the first way, which will actually be a little bit more challenging, and then looking at a shortcut by using the diagram that I showed you on the previous page. So let's evaluate the first function here, arc cosine of 1/2. So arc cosine of 1/2 equals some output, which the output of an inverse trigonometric function is an angle. So we'll call that angle theta. But this theta that we are finding has to be between 0 and pi inclusive. But this means that cosine of theta is 1/2, and theta is between 0 and pi. This means that theta is equal to pi over 3. So cosine of arc cosine of 1/2 is the same thing as, and I'm going to replace arc cosine of 1/2 with what we just found it to be, pi over 3. Now what is the cosine of pi over 3? 1/2. So let's take a look at it by way of a diagram. So I have my two circles, my inputs and my outputs. And in the first circle I put my angles, and in the second circle I have my ratios. And I get from my angles to my ratios by way of a trig function. So what's the trig function here? Cosine or arc cosine? Cosine is the trig function. And then I get from my ratios to my angles by way of the inverse trigonometric function mentioned, which is arc cosine. So I have the input of 1/2. Where does that go? Well, that's the input of the arc cosine function. And the input of an arc cosine function is a ratio. So that should go in the ratio circle. So we are going to input 1/2 into the arc cosine function, and that's going to output an angle. What angle does that output? Well, it has to be in a restriction, which we talked about in the first method. It has to be between 0 and pi. But let's just call it theta for a moment. I don't necessarily care precisely what it is. It's an intermediate step. So now that I have that angle, I just have to find the cosine of that. And cosine of that theta has to be 1/2. So I end up where I began. So we know that cosine of arc cosine of 1/2, well, the cosine will undo the arc cosine, and we end up back where we began. In our next example, we have arc sine of 0.85. So let's go ahead and draw our diagram. So this is the same diagram that I had on the bottom of the previous slide. And we have angles over here, and we have ratios over here. And angles go to ratios by our trig function. And our trig function here is sine. And we are going from our ratio to an angle by our inverse trigonometric function, which is arc sine. And so what is our input of arc sine? The input of arc sine is 0.85. In which circle does that go? Well, it's the input of an arc sine, so the input of an arc sine goes in the ratio circle. Now, we don't actually have to figure out what the angle is that goes to. So we can call it, say, theta. So if we do that, then the output of arc sine is some theta between negative pi over 2 and pi over 2 inclusive. Now if I take the sine of that angle, I will end up, without restrictions or anything, in the 0.85 category. So the output of this is just 0.85. Sine will always undo arc sine for any value that is appropriate in the domain of the arc sine function. So as we look at our next example, let's begin by drawing the circles once again. I have my angles, and I have my ratios. And here my angle is taken to my ratio by the sine function. And I'm taken from ratio to angle by the arc sine function. So the input of the arc sine function is a ratio, so that's where the negative 1/2 goes. And then it outputs some angle. Now there is a restriction on that angle. Because negative 1/2 is a ratio that we know from our special triangles, we could determine what theta is here. But do we have to? We end up with some restricted angle, but then we apply the sine function, and we should get back where we started. So our answer is negative 1/2. If you wanted to, you could go through this problem and actually figure out what that angle was. So if we look at simply the inside of this function, this composite function, arc sine of negative 1/2 outputs some theta. That means that sine of theta equals negative 1/2, where theta is between negative pi over 2 and pi over 2. Now, you can pause right there for a moment and just see where what we just did in the first method is clearly the answer. But if we want to go through and actually determine the theta, we can. So, what is the angle theta? The angle theta that we're looking for has to be between negative pi over 2 and pi over 2. But here sine of theta is negative, so that must mean that we're in the fourth quadrant. So we're between negative pi over 2 and pi over 2. So the reference angle is pi over 6. If I just disregard the negative for a moment. Now, how do I get in the fourth quadrant? Well, it's either going to be 11 pi over 6 or coterminal to that. But to be in the restricted range of the arc sine function, we have to be between negative pi over 2 and pi over 2. So that means that this should be negative pi over 6 to land in that interval. So that means that whenever I look at sine of arc sine of negative 1/2, this is the same thing as the sine of, and I'm replacing arc sine of negative 1/2 with what we just found it to be. So that would be negative pi over 6. What is the sine of negative pi over 6? It's negative 1/2. So let's evaluate arctangent of 5 pi over 4. So this one is different than the previous examples. You'll notice here our inside function corresponds to our trig function, and the outside function is the inverse trig function. So let's begin again by drawing the circles just to gain our bearings. So we have our angles and we have our ratios. And we're going to go from our angle to our ratio, and we're going to go from our ratio to an angle. And what takes us from the angle to the ratio is the tangent function. What takes us back is the arctangent function in this example. The key thing to remember here is that there is a restriction. What's the first value that we see? 5 pi over 4. That's the input of a tangent function, so that must be the angle. So if we start there, and I take the tangent of 5 pi over 4, I'm going to end up at a ratio. We go back to our angle, but you'll notice that we pass through that restriction. So the output has to be in line with the range of the arctangent function, which is negative pi over 2 to pi over 2. 5 pi over 4 is not in that range. So 5 pi over 4 can't possibly be the answer. So let's take a step back. We have arctangent of tangent of 5 pi over 4. What is the tangent of 5 pi over 4? Well, if we just look at the reference angle pi over 4, the reference angle for, or the tangent of that reference angle is tangent of pi over 4, which is 1. But 5 pi over 4 is in what quadrant? What quadrant are we in? 5 pi over 4 will be in the third quadrant. Tangent is positive there. So now we're looking at arctangent of 1. So the output of tangent is 1. Now we need to go back. So 1 goes to what angle? Between negative pi over 2 and pi over 2, what angle yields a tangent of 1? And the answer is pi over 4. So what you really do is you take 5 pi over 4, you trace it over here to the ratio that it yields, but then go back and you just need to find the representation of 5 pi over 4 within that restricted range of the arctangent function that would yield the same sign that 5 pi over 4 did, but had the same reference angle. So let's look at arc cosine of negative 7 pi over 6. Again, until I get my bearings, I'm going to draw this diagram because I find it helpful. You may or may not find it as helpful as I do, but this is how I think about it. Angle, ratio. And I'm going from my angles to my ratios here by the cosine function, and then I'm going back by the arc cosine function. Remembering that there is a restriction on the output of the arc cosine function. So what's the angle that I start with here? It's negative 7 pi over 6. Now, will it work just to say that my output is the same thing? Because doesn't arc cosine just undo cosine? And the answer is no. Because if I go from an angle to a ratio by using the cosine function, the output's going to yield a ratio. And whenever I go back, the arc cosine function will have to output something within its restricted range. So therefore, the question is, What is that angle? So let's look at the input of the arc cosine function. We have the cosine of negative 7 pi over 6. What is that output? Well, if I ignore everything except the reference angle will be pi over 6. So what is the cosine of pi over 6? It's root 3 over 2. Now, where does negative 7 pi over 6 reside? What quadrant? So, let's quickly do that. 7/6 is 1 and 1/6. So, this will be measured in the clockwise direction because the angle is negative. So I have 1 and 1/6. So 1 and 1/6 pi would be in the second quadrant. Cosine is negative there. So the output of cosine will be negative root 3 over 2. So now let's look at the arc cosine of negative root 3 over 2. The output of arc cosine is going to be some angle theta. But theta has to live between 0 and pi. Well, my angle has to have a reference angle of pi over 6. So let's look at cosine of theta equals negative root 3 over 2. But theta lives between 0 and pi. So what is the angle theta? Again, has a reference angle of pi over 6, but we're in the second quadrant, so I have to be just under pi to be in the second quadrant. So pi is 6 pi over 6. I back it up and make it 5 pi over 6. So the correct answer of this is that arc cosine of cosine of negative 7 pi over 6 equals 5 pi over 6. Now let's look at a little twist on these things. Here we have 6 pi over 5 as our angle, and the question is, this is not one of our memorized angles that we know what sine is. So let's go ahead and just take a look for a moment of our diagram one more time. So we have arc sine of 6 pi over 5. I go from angles to ratios and this time I'm going from my angle to my ratio by the sine, and I'm going back by the arc sine, and I'm starting with the angle 6 pi over 5. I don't know the ratio that yields. So I do know, however, that whenever I go back, that there is a restriction on that angle. So what is the angle that I go back to? Okay, so let's kind of put things in perspective. 6 pi over 5 will be found in what quadrant? 6 pi over 5 is 1 and 1/5 of pi. So 1 pi and then another 1/5 pi will land us in quadrant 3. So what's the reference angle? What is the measure of this acute angle here? Let's call it alpha. If our total angle is 6 pi over 5, then how much more did we have to go from pi to 6 pi over 5? And that was 1/5 of pi. So alpha is pi over 5. So now what does this tell us? Arc sine of sine of 6 pi over 5 is going to be related to the angle 6 pi over 5. But it's not going to be that angle 6 pi over 5. It will have the same reference angle. But now we have to figure out how to get that angle in the appropriate quadrant with the appropriate restriction. So it has to be between negative pi over 2 and pi over 2. So we know that arc sine outputs between negative pi over 2 and pi over 2. Quadrant 3, sine is negative. So how do we land really between here and here with a reference angle of pi over 5, but have a sine that's negative? So this is pi over 2 up here. This is negative pi over 2 down here. And we want an angle that is in that interval, but we know that sine has to be negative, so that's really restricting us now to this portion. Now we want an angle between negative pi over 2 and 0 that has a reference angle of pi over 5. And that is simply negative pi over 5. That has the appropriate reference angle, it's in the appropriate quadrant, it's in the appropriate interval. And so therefore, that is our angle. Now let's look at arc sine of cosine. So notice here that the inverse trigonometric function does not correspond to the trigonometric function that we are using. So let's draw our diagram. Here we have our angle of 7 pi over 6, and that's getting mapped to some ratio and then we're going back. So it doesn't make sense here to even think about undoing a function because we don't have that relationship between sine and cosine. So we move from our angle to our ratio by the cosine function, and we move back by the arc sine function. And we do so keeping in mind that there's a restriction. So let's go ahead and look at cosine of 7 pi over 6. Cosine of 7 pi over 6 is negative root 3 over 2. Right? The cosine of pi over 6 is root 3 over 2. 7 pi over 6 is in the third quadrant. So cosine is negative in the third quadrant. So now we're looking at arc sine of negative root 3 over 2. And that is going to be some angle, call it theta. But this means that sine of theta equals negative root 3 over 2, and theta has to be in the restriction, negative pi over 2 to pi over 2. So what angle yields that for us? The reference angle for this is pi over 3, right? Because sine of pi over 3 is root 3 over 2. But how do we get sine of theta to be negative and be in our restriction? So we want it to be between negative pi over 2 and pi over 2. So our answer is negative pi over 3. So arc sine of cosine of 7 pi over 6 is negative pi over 3.